And it is a pleasure for us to have the chair of the scientific committee with us again, Dr. Piero Fossati from Austron, who will be delivering a lecture on linear energy transfer painting. Piero, thank you for being with us again, and I give you the floor.
Thanks a lot. It's a pleasure, and I will miss you and this daily appointment. So, having said that, you have heard up to now mostly why we thought that carbon ion was a good idea, and what are the very interesting results that have been obtained so far. But we don't want to leave you with the idea of the wrong idea that carbon is a technology and the tool that has been explored to its full potential. We have quite a number of new things that we want to do with this tool. So you will hear during the course, and you've heard about some of these. And of course, this is not a comprehensive review, all the new things that we can do. But this LET painting, linear energy transfer painting, is indeed something that all the centers are interested, because it has a potential of improving our results further. So again, you have seen this almost to the nausea, but let's repeat once again. With photons, you have an exponential fall off because you have a lot of photons, and they have always the same probability of interacting. So in the first centimeter, 10% is absorbed, and then 90 pass. And in the second centimeter, 10% of the 90%, so 9 is absorbed, and 81 pass. And in the third centimeter, 8.1, which is the 10% of the 81% pass, blah, 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 and you get a nice exponential. But every photon is either absorbed in a shallow position or in a deep position, but one hit and the photon is lost. So it means that the quality of the damage that you are doing is very similar, because it's just a photon that by chance interacts early or by chance interacts deep. Yes, you might say that the probability of being absorbed is not exactly the same for photons of different energies, so you have this hardening or softening of the beam. Well, it's really completely negligible. So the point is, the damage is done by a radiation that is always the same. The radiobiological properties do not change. What gets those in the entrance or in the exit of the beam gets the same quality of those, not the same quantity, but the same quality. And again, we have said with particles, it's completely different, because one photon is very, very thin. Poor photon, it has not only a small mass, it has no mass at all. And there's only that amount of energy you can pack into it, but not so tremendous. So one photon will normally break one chemical bond. Yes, maybe more if you produce secondary electrons, okay, granted. But one photon, small amount of energy, and enough to break one chemical bond. But one heavy particles, it's heavy, even protons are, I mean, of course, if you say how many more times heavier than zero, infinite times heavier, but okay, forget that, much more energy in a single photon, in a single proton, or even more in a single carbon ion than in a single photon. So one particle will lose energy not in one shot, but in several events. So with particle therapy, we have that in the beginning they are fast, and the more energy they lose, the slower they become. And the slower they become, the easier it is for them to lose energy. So what does it mean that it's easier to lose energy? Well, of course, you lose energy because you break chemical bonds and because you produce secondary electrons. And in the beginning, it's harder to interact, but when you interact, possibly you produce a faster secondary electron, and in the end, it's easier, and the secondary electron will be slower, but the energy spectrum of the secondary electron is not really a big issue for us. And also the amount of fragments that you produce, of course, is not exactly the same, but it's not really a big issue. The big issue is just how many chemical bonds are broken per unit of length. So when you are here very fast, you deposit little energy, and the little energy you deposit because in 1 micron, you don't break so many chemical bonds. And here, where you are very slow, you break a lot of chemical bonds. So the density of ionization, we have said it and we will repeat it once again, is less dense in the beginning and more dense in the end. But with protons, even when you are very dense, you are still not dense enough. So even at the very last part of the proton beam, except here in the very, very, very last part, the mean distance between two ionization events, between two broken chemical bonds, is much bigger than our unit of measure, which is the DNA double helix. So you can make a small mistake, a small approximation, and you can say the radiobiological properties of proton do not change over the path, which is not true, but is true enough to be used in the clinics. Instead, with carbon ion, this is completely false. Here in the entrance plateau, you have a sparsely ionizing radiation, and here in the end, you have densely ionizing radiation, and that's the reason why we use carbon. We use carbon because we want to have as good as protons in terms of conformality of dose. So the break peak, so no exit dose, yes, a little bit for the fragmentation, but not so much. Little entrance dose and a lot of dose in the tumor. And on top of that, we want to have the same good safety profile for organs at risk that are upstream as protons. So we want that the quality of radiation in the entrance channel is like sparsely ionizing low LET, and we want to have the same high efficacy of neutrons in the tumor. So ideally, it would be nice to have a particle that has completely sparse ionization until the tumor, and then tuck in 1 micron or in 1 nanometer converts from sparse to dense. Well, of course, it's not like that. And the idea is that carbon might be the best option to give a lot of high LET, dense ionizing radiation to the tumor, and just a little bit in the healthy tissue. So is this true? Well, no, it is not true in reality. That's the whole issue. It is true only for very small objects. When you do radiobiological experiments, then you typically irradiate small things, small samples, monolayer of cells, very, very, very thin, or tumor in the leg of a mouse. And again, you might have noticed that a mouse is smaller than the human being, and the tumor growing in the leg of a mouse cannot really be a 10-centimeter tumor. There's simply not enough room. So what does it happen when you don't take these artificial radiobiological models, but you take real tumors? What happens is that most of the tumor, if you treat with carbon ion, is not really getting high LET. So look, with protons, well, even the high LET is so low that we are ashamed of calling it high LET, that is the single SOBP with one beam coming from the left of the screen. So in the entrance of the SOBP, you have very little stopping particles. Most of the dose is delivered by the plateau accumulated of other particles, and in the distal part, you have a lot of stopping particles. So what is the LET? Well, with protons, it stays low throughout, and with helium, almost the same. So that's why we are saying, yes, you can use helium like a proton with a sharper penumbra, because indeed, the higher LET of helium is not so high. This is all to be proven in reality, but that's the qualitative thinking behind helium. And if you take carbon, and if you take interesting levels, so interesting levels is 40, 50, or 80, or 10, or 100, then you will see that really high LET, that kind of high LET that will result in little or no oxygen effect, little or no effect of viability of apoptotic pathways, little or no effect of fractionation, all the things we have described as the property of carbon, well, they are true maybe in the last centimeter of the tumor. And if you want to have more high LET, well, yes, of course you can, but you have to go heavier than carbon. So carbon could have been, in theory, the optimal option for small tumors. Well, we are arguing now if oxygen would not be a better option for big tumors. But carbon we have, and we have 30,000 patients, and we have more than 20 years of clinical experience. And oxygen, yes, it is there. We can use it. We want to use it, but clinical experience is close to zero at the moment. So, okay, we are not treating really with one single beam. Let's look at something slightly more realistic. What is the dose average LET of carbon beam optimized in a clinical way for simple geometries if you take two beams? And this, again, you have seen, but let's spend a little bit more time on that. If you take two beams, then every optimizer will work in this way, that each of the two opposed beams will be allowed to go all the way to the other side. And that's the best way to optimize, because if you think about it, then the target will get the contribution of a, let's say, SOBP-like dose of 2 beams, and the entrance plateau will get the contribution of the entrance plateau of only 1 beam. So if you want to give high dose in the target and low dose in the healthy tissue, the best way is use every beam to overshoot to the distal edge of your target. So you are maximizing the contribution in the tumor and minimizing the dose in the entrance plateau. And if you do that, again, the very effective particles will be normally at the border between the target and the healthy tissue. And in the center, you will have a valley where you have entrance plateau of one and entrance plateau of the other, and they add up. So how high is the LET in this valley? Now, at this point, you should all be familiar with LET, but let's take one step back and say again what it is. LET is not something we can measure. It's just something that we model. It is linear energy transfer. So it is the amount of energy lost by the radiation in just a very small unit of length. And we typically describe it in kilo electron volt per micrometer. So when we look at these numbers, 40 means that in 1 micrometer, whatever particles was coming in will lose 40 kilo electron volt of energy. Now, in reality, LET is made of several components. We have said, and let's repeat it again, with carbon ion, when you start in the accelerator, you just have carbon ion. But when you end up in the patient, you have a mixed field of particles, which is made of primary, so carbon ion, carbon 6+, of different energies, and they behave completely different in terms of LET. Once again, slow carbon, so almost at the end of the path, high LET, fast carbon, so entrance plateau, low LET. Why in a voxel you have a mix of fast and slow? Because you have particles stopping there and you have particles passing by to stop elsewhere. And then you have all the fragments that have been produced by carbon stopping close and by carbon stopping far away. And we know that fragmentation is really extremely important in carbon ion. You lose lots of primary to fragmentation. And typically fragments don't really scatter only straight, they go also laterally. So in one voxel, you will have a lot of different components of those. Each of these components of those will have its own LET. How can you describe this? You describe it as an LET spectrum. Well, indeed, LET is not related one-to-one to density of ionization. This is specific for the particle species. So what you have to do is not only describe one LET spectrum, you have to describe multiple LET spectrum of all the incident particles. Primary carbon and fragments. Fragments go from carbon 12, carbon 10, carbon 11, down to protons. All this stuff you have to describe, and then you will have a LET spectrum. So you will say, I am delivering in this voxel, I don't know, 3 gray. Out of these 3 gray, how many grays are delivered between 0 and 1 keV per micron? 0.1. How many are delivered between 1 and 2 keV per micron? So you have a curve, a LET spectrum. And what you do, you describe all this information, which is a spectrum, with just one number, the dose averaged LET. So this is just simply the center of mass of the LET spectrum. So this that we display here is the dose averaged LET. And as you see, if you have a small tumor, 4 centimeters, and 2 beams kissing each other from 2 different angles, from 2 different opposite directions, yes, you have peaks of high LET at the border, but even in the middle, you stay around something that we can call high. So those average LET more than 50, we can live with that. But if you increase the target size to 8 centimeters, then in the middle it goes down. And if you increase it even further, it goes down more than that. So when we are treating a tumor with carbon ion, size does matter. Like in the Godzilla movie, a big tumor will get carbon ion that looks like carbon ion. So I'm sensitive to fractionation, to oxygenation, to viability of a apoptotic pathway, to stemness, to radioresistance, to quiz, the reason why we are treating with carbon. But if we treat a big tumor, then the middle of it will get carbon ion that look like protons. So they don't have the good properties we would like them to have. Does it matter? Yes, it matters a lot. So this was the starting point. There were papers from Japanese colleagues, and they were saying, well, we can do something that no one else in the world can do. We can cure, not just palliate, we can cure inoperable osteosarcoma, horrible disease, and whatever other serious you look, 5-year survival of osteosarcoma that cannot be resected surgically is 0. Why cannot it be resected surgically? Because it is in the spine, it is in the sacrum, it is in the shoulder, so it's not in the limbs. Normally osteosarcoma is in the femur, in the arm, and then you can cut it out with good margins. But if it is in a nasty location where the surgeon cannot cut it out completely, then you simply don't cure this patient. Only possible exception is small children in which chemotherapy can have some potential, but we are talking of really something like 5% survival at 5 years, even in these children. But adults with osteosarcoma that is not resected, they cannot survive at 5 years. There's no chance. And we have this Japanese data with wonderful results. So you can control osteosarcoma with carbon ion used instead of surgery, and this patient can survive, and survival at 5 years is in the 2 digits. So this was one of the strongest case for carbon. And what is relevant to us is that there is a huge difference if you take a big tumor or a small tumor. If you take a tumor that is more than 500 cubic centimeter or bigger than 500 cubic centimeter, you can see in the upper left in the A panel, the local control of a osteosarcoma of half a liter, which is by no means small. It is still a disease that would kill all the patients. But you can have local control in the 80% or something like that. And if it is instead a big tumor, local control goes down to 20%. So there is a huge difference. Well, this was the arguments we were using to say big tumors don't get high LET, so you call it carbon, but it's not like it's really carbon. So we have to change something. And of course, there was a potential objection saying, no, this is just your fantasy. Big tumors are worse than small tumors, and that's the full story. So it's just because, well, we were at that point, and this was like 10 years ago. You see, this is 2012, this paper. We were saying, yes, but look at survival. The difference in survival is smaller than the difference in local control. This cannot be. It must be really something related to the LET in the big tumors. Otherwise, I understand big tumor is worse, but how comes that this is even worse for local control than for survival? So this was a little bit the status of the debate. And at this moment, we are accumulating evidence that indeed a big part of this huge difference in local control when you compare big and small tumors has to do with LET effect. So this is a paper by the Japanese groups in NIRS QST, in which they are analyzing tumors according to the volume and according to the portion of the tumor that is receiving enough high LET, high LETD, those average LET. And what they see is that, of course, it's easier to cure small tumors, but that recurrence is really always in tumors that are in the low LET group. So if you do not put the high LET in the tumor, then you don't achieve carbon-like results. So this was a confirmation that yes, indeed, LET is, if not the only, at least a very important reason why you are not achieving this good local control in large tumors. And then they said, let's look at other entities, and they checked again the group from NIRS, the predictors of local recurrence in pancreatic cancer. As you have heard, there is a very interesting program of pancreatic cancer treatment with carbon, using carbon instead of surgery. This is something that is extremely difficult to do, and you will hear tomorrow that there is an effort to transform the Japanese experience into an international trial. But at the moment, it is mostly Japanese experience about pancreatic cancer. And they analyzed what's happening. And what's happening is that there is no correlation and no predictive value in terms of RB weighted dose and recurrence. So the patient that had a recurrence were not undercovered in terms of our model of RB weighted dose. But there is a quite strong correlation and predictive value between low LET in the target and recurrence. So we thought it was relevant for big sarcomas. Well, maybe it's relevant also for small tumors, especially when you have very challenging anatomical situation like pancreas. That's always challenging. A tumor needing high dose and duodenum that you can damage in a bad way, and then the patient bleeds and dies. So you have to be very careful how you put your spots and your beams. You cannot do what you want. And the result is LET goes wherever it goes. You don't have a lot of control on that. So if the high LET goes into the tumor, good. You have much better options in terms of achieving local control than if it doesn't. And then we said, yes, maybe this is an issue with the MKM model. Well, no, it is not with LEM, and this is data from now. It's just the same, looking at the sacral chordoma and at recurrence. Well, the recurrence were not really correlating with coverage in terms of LEM RB weighted dose, but were correlating with coverage in terms of being able to put high LET. So my point is high LET in the tumor is something that really matters, and there is not causality shown, but there is correlation shown, and different RB models, different tumor entities, different continents, we all consistently see that low LET in the tumor means higher risk of local recurrence. How can you react to that? Is it something that you can change? Yes, you can change, and you have very many options to change it. So you can try to put the high LET where you want, and you can try to do even other more complex things. So at this point, there is a very crucial thing to be discussed. I often have discussion with colleagues that say, well, if the RBE weighted dose is not predictive of the outcome, it simply means that our RB model is not good, and then we need a better RB model. And I think it is not the way to go, because we are simultaneously interested in many endpoints, and most of them are unknown. And then, of course, there is the point of view which you must have if you are a scientist. What is unknown today will be known tomorrow. But my point of view is that no, it will be unknown also tomorrow, because there is intrinsic heterogeneity in the characteristic of tumor. So it is extremely optimistic and naive to believe that we will know where are the cancer stem cells inside the tumor, where is the day by day and minute by minute variation of hypoxia, etc., etc. So either you acknowledge that all your endpoints are random variables and not a random RB model, but then it becomes a nightmare for optimization. Or, and this is the way I am always advocating, you acknowledge that there is nothing such as a perfect RB model. You can use LEM, you can use MKM, even better, you can use both of them. And instead of looking for a third, a fourth, a fifth better RB model, we should say RB is not the full picture. We cannot model all the relevant variables, but we know that the high LET component is intrinsically more robust against all of them. So rather than trying to find the better mix of low and high RB that makes it equivalent, let's simply say we must put the high LET in all the tumor. So the kill painting is a clever attempt to say, I will go for uniform cell killing, but this is based on the assumption that you can really know in great detail the voxel by voxel response curve of cells. And this is unknown also because it changes patient by patient, voxel by voxel, day by day, because of the intrinsic heterogeneity of tumor. So this is a very interesting theoretical approach, but I think we should just stick to a simpler thing, and this: don't try to model what you will not be able to model, but acknowledge that instead of modeling, it's better to use the part that you know is more robust against all the non-modeled one. Now, there is a big open issue, and the open issue is, assuming we agree that it is important to steer both the RB weighted dose, but also the low-level physical quantity. Can you do it with one particle, or do you need multi-ion? Do you need multiple particles to be delivered in the same fractions? And of course, multiple particles will give you an additional a degree of freedom, because you can use oxygen, let's say, to treat the center, and then you can use a lighter weight particles, maybe helium, to cover the border. So you can shape your LET much better if you have more tools. But what we are at the moment investigating is, do we really need to wait before we have multi-ion therapy clinically available? It's not a short and easy process, and it will not happen tomorrow. It will not happen in the next year. At the moment, I believe both German and Japanese facility are investigating that, but it's still unknown if and when we will be treating patients like that. So can you do the same just with carbon, using only one particle? And the big concept is, you should put high LET in most tumor voxels. But this is just the very naive qualitative thinking. What does it mean high LET? What does it mean most tumor voxel, and how big a part of the dose must be at high LET? So what we are trying to do at the moment is, we are investigating the plants that have been optimized without any special care to LET, and we are investigating what happens to those plants when we compare tumors that we know are faring poorly, so big sarcomas, and when we compare tumors that we know are faring much better, so small sarcomas. And we are trying to find out what is the difference in terms of LET distribution, what is the best parameters that differentiate small and big tumors. This is an ongoing project, and if we manage to finish this project, we will come up with numbers to that qualitative statement, and then we will say, well, you need to have, let's say, at least not more than 27 cc or something like that of the tumor, so the coldest LET part that must be covered with, let's say, 40 or 50 Kep per micron of those average LET, something like those numbers. And then we will be able to test these parameters in some independent data sets and say, is really important the big versus small and the impact of LET? Are those parameters derived just from size? Are they going to be predictive of recurrence? So this is what you look if you just have a normal plan. Here we have a sacral chordoma. We made concentric contours. The LM RB weighted dose in the left-hand side is very homogeneous, wonderful DVH, almost perfect, almost square. The MKM recomputation shows that you have cold spots and hot spots, and that the LET, the dose average LET, shows that the very high dose average LET is not really where you want it. It's wasted at the border between the target and the healthy tissue. And quite interestingly, this confirms what we know, so that the MKM is treating high LET with more respect. MKM model is describing the high LET as a very important part and gives a high premium to RB where there is high LET. And LEM instead is a little bit more egalitarian. So it says, yes, high LET is more effective, but in the end, not so much more. So what you see is that high LET part of the plan are the parts where MKM dose is higher. We know that with moderately hypofractionated schedules, so 12, 16 fractions, so LEM prescription dose 3.6 to 4.4 corresponds to a higher, MKM prescription dose 3.6 to 4.4 corresponds to a higher LEM prescription dose. So we go from 3.6/4.4, we go to 4 up to 4.8. So you expect to see lower dose when you take a LEM plan and recompute with MKM. This is true in the largest portion, but it's false where there is a lot of high LET. So of course, the MKM is less steep as a DVH for RB weighted dose, but we have now very easy to use tools in commercial TPS in which you can look at the three together, one model, the other model, and the LET. We were really looking at two things, as saying, what's the difference between big and small tumors, and what you can do in theory to change that, to make not only the RB weighted dose of a big tumor to look nice, but also to make the LET distribution of a big tumor to look nice, or at least as nice as that of a small tumor. And at the moment, we are investigating two options. So of course, the third options, which we are not investigating, which is the more elegant, the best one is multi-ion optimization, but this is a bit far away in the future. What we are trying to do is just use carbon that we have and use it in a different way to achieve our goal of putting the LET where we want. So if you go for optimizing the LETD, you just ask to the optimizer to do that. And in the commercial platform we are using, it is available, but not in the clinical version. So clinical version you can do for protons. We are waiting for carbon, but for research purposes you can do. Or what you can already do is the poor man LET optimization. So you just put blocking structures and you say the beam is not allowed to overshoot all the way to the other side. And the interesting thing is that the RB weighted dose is not going to change massively. Is indeed not going to change massively if you have three beams. We are always hearing if you do LET optimization, you will significantly increase the dose in the entrance plateau. Well, that's just too simplistic. If you have three beams and you do dose average LET optimization with a formal tool in the TPS or with the simple blocking, if you have only two beams, it's true, but if you have three beams, what happens is very hard to predict. And in the end, it might be that you pay a very small price or even no price in terms of dose homogeneity and in terms of integral dose to the other tissues. And LET can really be steered. If you do nothing, LET is out of the target and close to the organs at risk. And what we found as a sort of a surprise is that the poor man version is not worse than the rich man version. So the real LET optimization is not always resulting in results that are much better of the blocking in terms of high LET inside the target. So again, this is in theory what you can do, and what should be your numeric goals. What would you call nice? I've put enough high LET in the target, and what you would call no, I've not put enough high LET in the target. For that, we checked a small set of patients, 22 patients comparing large and small sarcomas, and we found that just because the size are so different, well, it is not a good idea to look at relative DVH. You really have to look at absolute DVH. So this was a very easy, if you want, but still tricky part. When you look at relative DVH, 0% meets with 0% and hundreds meets with 100. And if you look at absolute volume DVH, then you have that 0 cc meets for all DVH, but they end up in different parts because one is 10 milliliter and one is 5,000 milliliters. But we were interested not in the hot part, in the LET hot, but in the cold. So the first thing is you have to realign the absolute value DVH not to 0 but to maximum tumor volume, and then you are not looking at the dose or LET at 1 cc, 2 cc, but you are looking at the dose or LET at tumor volume minus 1 cc, tumor volume minus 2 cc. And if you do that, and this here is not a DVH, a dose volume histogram, but it's an LVH, so an LET volume histogram, what we find is that there is a portion of the tumor that is behaving in a very different way. So there is a portion of the tumor in which the LET is much higher in the small tumors as compared to the big tumors. And we found that this is, and this is the first magic number of our analysis, this is 27 milliliter. So the big tumors are big because the most important part is that because they have up to 27 milliliter of tumor volume that is not covered by high LET. And also we found that the high LET we need to have results similar to small tumor is not so high as you would imagine from radiobiological experience, because these 27 milliliter of cold LET in the big tumors were really cold, less than 30, but in the small tumors were around 40. So at the moment we are saying, let's find strategies that allow us to have 40 kilo electron volt per micron, even in the coldest 27 milliliter of tumor. And this again is not coming from analysis of patients that did really relapse. So this is a work in progress, and our next step will be to test these numbers when they are finally finalized with some independent data sets and see if they are predictive of relapses. So how can you improve the LET in these 27 cold in terms of LET spots? Again, one option is LETD, the other option is blocking. And just look at how we are blocking. We are allowing some overlap of the lateral beams, and we are blocking the vertical beams to avoid it overshooting to the edge, but this is also work in progress. Should we allow 2 centimeters overlap, 1 centimeter, 3 centimeters? Should we block 2 centimeters in front, 3 centimeters? This again is work in progress. And you can really see how nicely you can bring back the high LET, which is all out of the tumor, and then you have it inside the tumor. So that the pink value is somewhat high, but the green value is already interesting. And apologies, now in the screen I'm not able to read them. Maybe you are, but I mean a green of 40, if I'm not mistaken, 40 kiloelectronvolt per micron can be given to most of the target by the simple blocking method. What was a bit of a surprise, and I think an interesting finding, is that by blocking, we can put more high LET into big tumor, even more than what you do if you don't take care of LET for small tumors. So there is a huge possibilities of improving the LET distribution. And the other thing that we found, and this was also a very, very nice surprise and somehow unexpected, we were thinking, if you do LET optimization, you will badly compromise your dose homogeneity in terms of RB weighted dose for the nominal length. But just because the high LET is also the hotspot with MKM, you will possibly improve the conformality of the MKM. Well, it was exactly the opposite. If you do it in simple shapes, maybe, but if you do it in real patients, you are able to improve significantly by blocking the high LET inside the tumor, paying basically no price at all in terms of RB weighted dose homogeneity in your nominal system, because your nominal system is what you are optimizing. And instead, you are paying a small price in the alternative system you use for recomputation. And there was significant improvement in LETD, both in the PTV, in the CTV, and in the GTV. The cold portion was much better with blocking as with normal. The other question that we asked is, are we going to get less high LET in the organs at risk? Well, apparently there was not such a big difference. Yes, the high LET in the organs at risk was less with blocking as compared with not blocking, but the doses were low, and for many organs, it was not such a striking difference. This is because we already know where is the risk, and therefore by reducing the RB weighted dose to organs like bowel and rectum, we are in a way protective. So this indirectly, this is all a work in progress, but this is an indirect confirmation that for carbon ion, the main focus of LET optimization rather than toxicity reduction is improvement in local control. Now, there are several more slides, but I think that they were there just in case we had a lot of time, and as always, this didn't happen, and this can be a very nice conclusion, and we stop here just to avoid going too much over with time, because the rest is about LET distribution in nerves, and this is very preliminary. So I would thank you all, and I'm happy to take questions.
Okay, thank you so much, Professor Fossati, for a very interesting lecture. We have two questions. You said that dose averaged LET was a center of mass of the LET spectrum. Which quantity represents the mass in your tractation?
the integral over all the LET from 0 to infinite, so the total mass. So basically, that's the physical absorbed dose.
Okay.
So if you
Second
have
question.
a LET spectrum, the area under the spectrum is physical absorbed dose, so the mass, and the center of mass, so the point where you can hang your spectrum and it will be in equilibrium, will not flip over. That's the LETD, the center of mass.
Okay, second question. Blocking method seems like you are separating a large tumor into several smaller subvolumes. Is this correct?
Yes. Not really separating because there is overlap between the two. We are just artificially avoiding beams to overshoot all the way to the other side. So we are stopping them inside the tumor. And separating would be left beam treats only the left part, right beam treats only the right part. No, most of the voxel inside are treated by multiple beams. So it's a separation with overlap.
Thank you very much.
We had no time to go into that, but of course a big topic is this separation resulting in gradients matching inside the tumor, is this less robust? And of course it is less robust. The question is how much less robust? And our point is that with carbon ion, you are never avoiding these gradients. So you have to find a balance between loss of robustness and improvement in LET.
Thank you very much. I am not seeing any other questions in the chat, nor am I seeing any hands raised.
I will stop,
Okay.
sir.
Yes. Okay, so Professor Fossati, thank you so much for this lecture, and we will see you again tomorrow.
Sure.
Thank you. Okay, so now we'll move on to our next speaker. It is a pleasure for us to introduce Slavisat Tuban from Austron, who will be delivering 2 lectures. In fact, the first will be on spatial fractionation, and then after the questions on that lecture, he will go into the heavy ion therapy integration with immune and target drugs. Thank you, Professor Tuban, for being with us, and I give you the floor.
Unmute. Okay, good.
Yes.
I'm sorry.
Yes.
I apologize.
Okay.
My computer stopped for a second, so sorry for that. So